Welcome everyone to this session. In the previous session, we looked at frequency acquisition in PLLs, okay, and we figured out that in type 1 PLL we could not acquire the frequency beyond a certain range. So, we introduced an integrator in the loop. I will show you the block diagram of the PLL which we discussed in the previous session. At one place we had a proportional gain which is with a gain tau p by tau I, and in the other path we have an integrator, and this integrator has gain 1 over tau I integral whatever function comes in that gets integrated, and these two things are summed up like this and it goes to the VCO. So, our loop filter is now replaced by the proportional n integral path, and at the end of the last session we looked at some simulated results where having only one path either proportional or integral does not help. So, this is your V error, this is your control voltage, and the voltage which you see at the output of the integrator is termed as V I, and this is V proportional, and we can say. So, in this particular example we have V in as sine of omega in t and V out as cosine of omega out t, and what we have is omega in is equal to omega at time t equal to 0 and omega out is equal to omega free, and this frequency error at the beginning omega in minus omega out, which is omega minus omega free, is delta omega at time instant t equal to 0. When this frequency error is large, then type 1 PLL was unable to acquire the frequency. What do we mean by acquiring the frequency? That the control voltage develops in such a way that the output frequency is finally equal to the input frequency, and there is the phase error is also settled. Okay, it does not change with respect to time. So, the things which we also discussed earlier were that initially your V error develops has some kind of asymmetric beat note like this, which has an effective DC voltage which I called as pull in voltage. This voltage was pull in voltage V p, and this V p DC voltage or the DC part of that voltage was actually integrated by this integrator, and it develops at the very end it develops a DC voltage here. In steady state, in this case in steady state, or if you want to call it at time t tends to infinity, at time t tends to infinity, what you are going to have is control voltage V c will be equal to your delta omega which you see at the beginning. So, I will make here delta omega 0 divided by k VCO, okay, in the final state. And when there is no frequency error in the loop and you have this integrator, the error voltage V error is going to be equal to 0. V error will be 0, integrated output will be equal to whatever DC voltage is required for the oscillator to compensate for the frequency error. V error voltage is going to be equal to 0, because if you have any non-zero DC value, any non-zero value at V error, then this integrator will just keep on increasing. So, oscillator will not be locked. So, this is not possible. Okay. So, this is what we figured out, and we have seen the waveforms at different locations also, right. Now, one important part here is the following, that without the proportional path you do not have asymmetric beat note, without the integral path you do not have large gain. So, both the things are required. If we happen to just analyze this PLL using its small signal model, then also you will see it is very important to have both the integral and the proportional path. By the way, just to highlight it, what is integral path and what is proportional path? This path is proportional path and this particular path is integral path. Okay. So, to make no confusion here, yellow one is the proportion, other one is the integral. Now, I am drawing the small signal model of the PLL. The small signal model of the PLL, you have the phase error detector with gain KPD. This is input phase, you have the output phase, and this particular block diagram actually can be used as such, but I will just write the transfer function here. This transfer function is tau p by tau I into 1 plus s times tau I, and it goes to VCO, which has a gain k VCO over s. Okay. So, this is the small signal model of the PLL. So, in this small signal model of the PLL, this is phase error, this is voltage error, and this is control voltage. The loop gain of this small signal model of the PLL is KPD times your loop filter transfer function, which is 1 plus s times tau p divided by s tau I and k VCO over s. Okay. So, to understand the need of the proportional path in this particular PLL, we can see that from the loop gain analysis also. In case we only had integrator, okay, integrator, which in turn means tau p is equal to 0, our loop gain would have been KPD times 1 over s tau I and k VCO over s. For this particular loop gain, let me call this as loop gain 1 and this one as loop gain 2. For loop gain 1, you will find that this particular loop is unstable. Why it is unstable? You can plot the magnitude of the loop gain. So, I will plot magnitude of the loop gain. You are having KPD k VCO by tau by s square tau. So, this is just written like this, by s square tau I will write this as k by s square tau I. Okay. So, your loop gain 1 is like having a fall of minus 40 dB per decade. Okay. This is omega, this is magnitude of loop gain in dB, right. The corresponding phase for the same loop gain, right. If you look at the phase of this particular loop gain, what you have is always minus 180 degree. So, I will just start here, let us say this is minus 90 and this is minus 180 degree. So, this is always, this is the phase for angle of loop gain. Let me just put this as blue. Okay. So, what you see here as the phase margin for loop gain 1, our phase margin is actually 0. How do we look at the phase margin? We look at the phase margin at the unity gain frequency. What is the phase, how far is your phase from 180 degree at unity gain frequency? That is how we measure the phase margin. The phase is always 180 degree, phase margin is 0. In other case, for loop gain 2, you see that this is kpd times kvco divided by s square tau I into 1 plus s tau p. So, you have a 0 at 1 over tau p. Okay. So, in case we place our 1 over tau p lesser than the unity gain frequency, your loop gain 2 will be something like this. It will start with minus 40 dB per decade, and after the 0 frequency it will be minus 20 dB per decade. So, this is omega z for loop gain 2. Omega z is equal to 1 by tau p. Okay. And the unity gain frequency will also change. The phase for the corresponding loop gain is going to be, it will start with minus 180 degree, it will go to minus 135 degree, because a 0 will give you a 45 degree heads up, and then finally in the end it will reach to minus 90 degree asymptotically. Okay. So, the phase margin for the new loop gain or loop gain 2 is this much. Okay. So, phase margin in this case is equal to, what is this phase value? This phase value is minus 180 degree plus tan inverse of omega by, so we are calculating this as omega u 2 by omega z minus of minus 180 degree, which is nothing but tan inverse of omega u 2 by omega z. So, you have a positive phase margin, your system is stable. Okay. This system is stable, whereas loop gain 1 it was not stable. Why it was not stable? Well, phase margin is 0. Okay. So, from your basic system level analysis, you would know that in order a closed loop system is stable, you need to have a positive phase margin, right. So, coming back to this small signal analysis and how we related it to the large signal frequency acquisition. There are, we will make two statements here. First, to acquire the frequency, when you have a large frequency error in the beginning, you need both proportional and integral path. You cannot do with only proportional or only integral. Second, from the stability point of view, right, the small signal analysis tells us you cannot have a system with two integrators stable, you need to have a proportional path for sure. Okay. So, both the analysis are telling you that you need both proportional and integral path for frequency acquisition and for stability point of view. Now, once we know that okay, the system is stable and the PLL we can acquire any frequency, the question arises, okay, now how much frequency error can be, how large can delta omega 0 be in the first place. So, the question which we are asking is how large, okay, we can have as the how large is delta omega 0. Okay. The answer to that question, you can do a rigorous mathematical analysis, but before doing the mathematical analysis we will just try to see what is limiting here. The way this particular PLL works is it can generate any voltage Vi, because it is just like an integrator. You give, even if you give a very small input to an integrator, right, over a given period of time it is going to generate whatever voltage you need. You give more time to an integrator, it will integrate a larger value. So, it can generate any voltage, and in a steady state this loop filter can have any voltage which you want at your output without having a non-zero input voltage. So, having a 0 here and a non-zero Vi, okay, whatever value you need, that is practical, okay, you can always get it. If that is the case, then it does not matter what is my initial frequency error. At the end, if this loop is in closed loop, it is going to acquire any frequency which you need. Okay. So, there is no limit on delta omega 0, actually delta omega 0, your pull in range tends to infinity. Okay. There is no limit. In practice, what you will see here is that if there is any limit on the VCO. So, what do we mean by that? So, in case if you are looking at the VCO characteristics, you may find that the omega out frequency versus the control voltage has some upper limit. We do not know how much. You cannot just keep on increasing the oscillator's frequency as you want. It may saturate at some point. At the end of the day, you will design these oscillators and all these blocks in a given technology. You know that you cannot increase the voltage beyond a certain value in a given CMOS or BiCMOS technology. So, your frequency is always going to be limited by that at least. Okay. So, this loop itself does not put any restriction on the output frequency. Mostly the output frequency restrictions are added by the VCO or some other block, maybe the loop filter or any other block. Okay. So, that is what we have. Your pull in range here is infinity, and if pull in range delta omega pull in range is that this tends to infinity, your hold in range also tends to infinity. Now, the question comes is, let me just write this as pull in range and this is hold in range. The other one was the lock in range. So, for this particular PLL, we have seen that the lock in range requires the phase error to be limited within 2 pi and acquire the lock. Okay. So, for lock in range, what you need to do is you need to find out the frequency range to which the PLL locks without the phase error exceeding 2 pi, right. And we have seen that the PLL locks without the phase error exceeding 2 pi, it can do that only through proportional path. If the integral path does not require to develop any voltage, the proportional path acquires the lock which we have seen earlier, then you will not exceed the phase error of 2 pi. Okay. So, that limit will come from the proportional path, and delta omega lock in, this is equal to the same analysis only for the proportional path. This is going to be kpd times tau p by tau I, this is proportional path gain, times k VCO. Okay. This is lock in range. Okay. Does it matter that the PLL has a less lock in range and more pull in range? Well, if you are only looking for the frequency equation, it does not matter whether it is doing a cycle slipping or not. If you are looking for some other characteristics during the settling of the PLL, where some other block depends on this PLL frequency acquisition, then it may matter whether your frequency, whether you are doing cycle slipping during frequency acquisition or not. Otherwise, when you run the PLL, if it acquires the lock, that is good enough. Okay. So, now if it is so simple, then well, the PLL is done, but that is not the case. So, what happens is when you go ahead and you try to implement this loop filter tau p by tau I plus 1 over tau I integral dt. Okay, this is our transfer function in time domain. In Laplace domain, it translates to tau p by tau I into 1 over tau I s. Okay. So, this transfer function can be easily implemented by using an active integrator as shown to you like this, where I have this r and c providing me the integration here. This is you can say V error, this is V c, okay, and this particular resistance happens to be R1, this is R2 and this is C. So, assuming the amplifier is ideal, assuming your op amp is ideal, what you will see is that V c by V error in Laplace domain happens to be simple, you can just work it out. So, let me just help you with this. So, if this amplifier is ideal and this whole op amp with integrator is used in the PLL loop, there will be overall negative feedback for this loop filter, and I can assume that this node will also be incrementally grounded. So, you will have V error minus 0 divided by R1, that is 0 minus V c divided by R2 plus 1 over S c, okay, which implies that V c is equal to, you can just calculate all these things, V c by V error is equal to 1 over S c R2, right, divided by S c R1, and there is a negative sign. Well, now you can say previously this loop filter did not have any negative sign, now I have a negative sign. If you have a negative sign, do not worry about it. The way you are going to connect to the VCO in that particular path, you can adjust this negative sign. So, what is important right now is only this part. Okay. So, here you see that this I can write it as minus 1 plus S tau p by S tau p divided by S tau I, where our tau p happens to be 1 over C R2 and tau I happens to be, okay, so no, this is not 1 over, this is C times R2 and this is C times R1. So, given this loop filter, you can very well implement, you can add this loop filter here and everything seems to work. The problem arises because this loop filter which you are seeing here does not find an ideal amplifier, the amplifier happens to be non-ideal. So, we will introduce only one order of nonlinearity here, that this has a gain A. Okay. So, this is even a very simple nonlinearity, that the gain is fixed across the frequencies and the gain is equal to A. If you have this, then V c of S by V error of S is equal to minus A times 1 plus S tau p divided by 1 plus S tau p into 1 plus A times S tau I. Okay. If you want to do a sanity check, what you can do is you apply A tends to infinity. If you apply A tends to infinity, then in that case what you will see here is it should translate back to the previous one, right. So, if I apply A tends to infinity, I will divide by A on both the sides, numerator and denominator, which will leave 1 plus S tau p, divide by this term will also see divide by A, here one term will see divide by A. So, you will have S tau I. So, as a tends to infinity, it does translate to the transfer function. Now, in the presence of this new transfer function which you see, Vc of s divided by V error of s, which has some DC gain and the other part, right. This loop filter transfer function I am just writing as loop filter of s right now. It is not so simple to define the pull in range and the hold in range. Okay. Well, if I want to draw this loop filter, I can very well draw this loop filter here. It has a DC gain, loop filter of omega. The DC gain of this loop filter happens to be A, okay, and then it has a pole at 1 divided by. So, the pole for this loop filter transfer function happens to be at 1 divided by tau p plus 1 over a tau I. So, you will have a pole here, okay, and then you have a 0 and 0 happens to be at 1 over tau p, which is going to be much farther away, and after the 0 it will have flat. Okay. So, you will have at 0, after the 0 location, you will see a flat response. This is omega p, right. And what is this value? You can find this value as s tends to infinity. You can substitute in the loop filter transfer function as s tends to infinity. So, I just want to find loop filter of s as s tends to infinity. Well, you can very well write it like this, okay, minus 1 plus tau p divided by 1 by s plus tau p, okay, plus you have 1 plus a times tau I. Okay. So, this happens to be minus a times tau p divided by tau p plus 1 plus a time by tau I, and under the fact that a tends to infinity, right, you can do it that way, as a tends to infinity, this is nothing but tau p by tau I. So, this is what I have here approximately, okay, if a is assumed to be very large, because for amplifier a is in general pretty large. So, what you see here is you do not have an ideal integration path. You have an integration path, but that it happens to be non-ideal, right, and then you have a proportional path with a constant gain like this. So, the loop filter which you see here can be written, the transfer function of the loop filter can be written as it is a times tau p divided by tau p plus 1 plus a times s, sorry, there is no s here, 1 plus a times tau I, plus the other value which is a into 1 plus a times tau I divided by tau p plus 1 plus a times tau I, and I will put all the frequency transfer function like this, which is same as earlier, 1 plus s tau p plus 1 plus a times s tau I. See, doing all this math is just to help you understand that when you have a non-ideal op amp, right, because of the gain of the non-ideal op amp, your actual loop filter gain changes, and then effectively I can call this, I can say this is like only a proportional path gain. Okay, this is a proportional path gain, and this is for a non-ideal integral path. Okay. As a tends to infinity, the gain of the integral path actually goes to infinity. Okay, but here the problem is a does not go to infinity. So, you have some kind of non-ideal integration. And what is actually non-ideal integration? To understand that, you can think, if I have a current source, right, and I pass it through a capacitor, I have this current source I pass it through the capacitor, the voltage V c, you will always see that this keeps on increasing. Whereas, if I go and add a resistor in parallel, let this resistor be very large. If this resistor is applied in parallel, and then I look at the time, the voltage with respect to time, if I applied this current source using a switch at time t equal to 0, you will see that this, depending on the resistor which you are having in parallel, this will keep on increasing. At the end, well, it will approach some value which is I times R, but this, depending on the resistor, right, it will keep on increasing. The final value is I times R. As R is large, the largest value which can achieve is, as t tends to infinity, is pretty large. During this time, the, you can say, over a period of time, it behaves like an integrator only. Okay. So, this is a non-ideal integrator which is mimicked by having such kind of transfer function. Well, you can also see that from here I V c by I in this case is nothing but R in parallel with C, which is your R divided by 1 plus SRC. It is similar to what you are having here. So, there is no difference, right. So, now given this non-ideal integrator, right, what is the pull-in range and what is the hold-in range? That is a very extensive mathematical exercise which I will avoid here. If you want, you can always refer to the books. Okay. What I can tell you here is that this particular pull-in range, having a loop filter which does not have an infinite DC gain, for loop filters with non-ideal DC, non-ideal amplifiers, or with DC gain which is not infinity, okay, for loop filters L of f in general, okay, we have to understand that how is this pull-in range defined. This pull-in range under many approximations happens to be KPD times KVCO into a square root of 2 times loop filter of 0 times loop filter of value at infinity. Okay. This is the pull-in range, and the hold-in range is KPD times KVCO into loop filter of 0. Okay. If loop filter of 0 is infinity, then you see that both the pull-in and hold-in ranges, they are actually infinite. So, pull-in and hold-in. Okay. I have not gone in the mathematical analysis of this, because that is quite intensive and it will be a sheer math exercise. Okay. So, we can ignore that right now, but you see that you have the loop, you have the pull-in and hold-in ranges depending on the loop filter value at 0 and loop filter value at infinity. Okay. So, now one of the loop filter which we have seen is an active loop filter. You can have a passive loop filter also. Okay. We will see in due course that which kind of loop filter is used in general, okay, depending on application. So, your application is quite important to decide what kind of loop filters you want, right. One couple of, I would say, assumptions which we have used in defining all these limits is that our mixer is a sinus. So, this pull-in range, hold-in range and lock-in range, right, all these things are they depend on our analysis, where we make some assumptions to simplify our analysis. Okay. And also this these particular limits are specific to the PLL which we are considering, where mixer is phase detector. Okay. Loop filter is whatever the transfer function it implements, we have that a specific loop filter which we are using. Okay. And VCO has no frequency limits. So, please do not use the same expressions for different kind of PLLs. Okay. It completely depends where we are looking at, okay, or what is the exact PLL, right. And our signals are sinusoidal, input and output signals are sinusoidal. Because later you are going to see that some of the PLLs, the input and output signals are square waves, and if you apply the same thing, it is incorrect. Okay. Other thing here is that if you think that this particular delta omega p, whatever value we have here, this particular value of omega p is the limit, and the moment you cross this, the PLL does not, the PLL cannot pull in. Well, these limits, above limits, are approximate limits. Okay. So, whenever you simulate the PLL and you find that okay, whether the PLL is not pulling in even for the frequency errors lesser than delta omega p, well, that is fine, do not worry about it. This is just an extreme, extreme limit based on many assumptions. Okay. So, please keep that in mind. Okay. So, thank you.